Everybody's in? Well, it is a honor for me to chair this last session of the inauguration of this very nice building, this splendid building where work and live splendid physicists that are our old friends since many years. They are fortunate because they will start this 2012 not only in a very nice building, but also in a moment in which LHC is starting to give new results. And I find again the pleasure of being in a field that advances. We had a long traversée du désert, we say, in which very little data had to keep our minds working. And now, fortunately, it seems that we will again feel the pleasure of finding new results, new challenges coming. As indeed you will hear from the first talk that Roeck will give on the highlights from LHC. Roeck, please. Yes, please.
Get the mic? Okay. All right, good afternoon. It's my pleasure to be here and to represent, if you wish, the experimental community for the inaugurational happening of this building. I hope it really generates lots of wise ideas in the future, which can find their way back in what we are doing at the LHC and elsewhere. And I guess my task is to ensure that it's always important to have data to be guided where things can be going. And as we will see, the LHC is starting exactly to do that. So it's highlights from the LHC. It's for a moment I thought maybe I call it the Higgs lights from the LHC, but then I decided against that title. But of course I will address that point. So, in your new building we have here, we have the collisions of the LHC. I will go through the following type of program. I'll give an introduction with a bit of warm-up on the standard model to show that there is more than just searches at the LHC. Then I go into the searches. Maybe the most popular one and most talked about one apart from the Higgs is supersymmetry. Extra dimensions I bring out because all the ADD people are in the room here. And there is conventional other signatures, some old ones like Technicolor or Z primes and all. I will be very brief on that to leave a bit of time for the second part, while going over new BSM signatures, so quite unusual signatures, things people said we haven't actually the right detectors for, but we will look at that again. And then, if the chairman allows, I will spend some time on the Higgs, and we'll see where far we get. So if anything happened on the way to Madrid, in fact, if you looked in the newspapers over the last few years, you see all these kind of things. This is just from the last 2 days. There is also a scientific page, which I have later relating to that, showing what's happening on the webs. And so what's the fuss is about? More about that later. So first, we talk about the LHC itself. I remind you, probably not too much needed, but what the LHC is. It's a machine, it's a hadron collider. Ultimately, we'll do 7 TeV on 7 TeV or thereabout. Maybe it's 6.5 at the end, we will see. Right now, we're running at 3.5 at 3.5 TeV. Maybe a little higher next year. These are the generic sort of topics from the prime physics program, but there is a lot of physics ongoing. In fact, both experiments, Atlas and CMS, the ones I will address most in this talk, have by now published almost about 100 scientific papers with results on a variety of topics from QCD, electric, and so forth, and I will pick out a few of that. So the LHC is a discovery machine, primarily, and it will certainly determine the future course of high-energy physics on the high-energy frontier. There are 4 central experiments, or 4 main experiments. There are in fact 7 experiments at the LHC in total, but 4 take a central position and interaction point. The others are smaller ones and they share with these interaction points. In fact, it's remarkable that the Spanish groups are involved in all of these experiments. maybe not so much in Alice a little bit, but certainly they are very engaged in CMS, which I know personally, obviously, and in Atlas as well, in big time, and also in LHCb they have been contributing to the hardware, the construction, the operation, and now particularly in the data analysis. I can testify that some of the Spanish groups are really leaders in our analysis part which we are having. So I think that would be a nice also collaboration between the TIER Institute and the phenomenology part of it and the experimental groups here in Spain, if not internationally. This is the history of the LHC in 2011. I will only talk in this talk about proton-proton collisions. There was also a heavy ion run at the end of the year, which was very successful too, which had 20 times the luminosity as what they collected last year. But this is really the remarkable part on the proton-protons. They have delivered to the experiments more than 5 inverse femtobarns, while, be it a bit understated goal which they gave at the end of last year was about 1 inverse femtobarn, which was already reached even before summer, and we could already use those data to produce results for the summer conferences. So that's what we have for LHCb on purpose due to luminosity leveling, because they don't want to have too much pileup events. They have collected less, so the machine could do that while they're giving the maximum luminosity for the 2 other experiments. And Alice is just a spectator in here for calibrating their heavy ion collisions. One can see that the performance of the LHC is actually also increasing, growing with time as you would like, but it's already quite high. In fact, this is a pie chart which shows what was happening with the LHC during the year, how the time was spent. And the thing you really want to look at is the green part, because that part of the pie here tells you how much time or what fraction of the time the LHC was actually delivering collisions to the experiment. So it's what we call stable beam at the accelerator. So that was about 23%, which is similar to numbers you had in sort of simpler machines like Leprosol, which were much more easy to operate. So already in the second year now of operation, this is an average reach, which is quite large. And you see the last 10 fills, in fact, we were like more than 30% of the time in collision mode. So, from the experiments, I will not explain in detail all the components of the experiments here. I will rather show the physics results, but just stress here that if you look, I mean, there are like 100 million channels here in these experiments, like Atlas and CMS. And here you see a chart of what fraction of these channels is actually alive. There is always some small issue with cables or problem here or there. And it's more than 98% for all subdetectors of all channels being alive. And since there is a lot of redundancy in these detectors, it doesn't matter if you measure a track with 10 points or 9 points essentially, there is actually no holes in these detectors apart from the beam pipes and maybe some small corners which are not behaving well. In all, we had an excellent performance both of the LHC and the experiments in 2011. The luminosity, the high luminosity number which we have, did not come for free, and this is the black beast, which you could say you could get when you're on the high luminosity. You get a high luminosity at this stage because they sort of overloaded the bunches more than what they thought they could do originally in the design when they run in the mode they were running now, which is only with half the bunches in the machine itself. And then we got to this high luminosities, but we got also two, like what was special this year is particularly the number of pileup events. This is the number of collisions you get within a same bunch crossing and happening somewhere along the bunch crossing line here. And they are recognized in large part through vertices which you see appearing. In fact, there are 20 in this picture if you calculate carefully. And so you have indeed 20 proton-proton, individual proton-proton events being produced during the same bunch crossing. Now, as you see, that can lead to a bit of a mess in the detectors, but in practice, many of these tracks are very, very soft, and so they don't actually bother too much. But it is a concern. There is always a sort of constant flow of energy coming in detectors, more than perhaps you would wish for some of the precision measurements. Now, this is not something the experiments were not prepared for. For high luminosity operation, that was always foreseen to go in the range of 20 to 25 pileup events on average. We are not quite there yet this year. We had only like 15 on average. The only thing is that perhaps we didn't expect it to come so early, but only in a few years from now. But we are there, and we have to deal with it. In fact, this can be turned into physics measurement by measuring and counting these vertices and these secondary, or the total number of interactions you get during a bunch crossing, and using the luminosity, you can actually derive the total inelastic cross-section from PP collisions. And that has been done, and that's a number which is coming out here. In fact, if you're interested in that kind of number, the best experiment which could give you that would be TOTEM. TOTEM is an experiment which is having forward detectors, which you see here. This is, in fact, very far. This is like 140 meters away from the interaction region. And they sit also in direction point number 5, the same interaction point where the CMS detector is. And in fact, due to using some information of CMS, namely the luminosity measurements made by CMS, and the elastic scattering cross-section, or the elastic scattering number of events counted in TOTEM, they could go to a total cross-section, not just a total inelastic one, but a total tout court, so everything included, elastic and inelastic one. And this is the number which comes out. This was always a question whether the cross-section would rise faster than the center of mass dependence, the square root of S dependence here, and apparently it seems to be well behaved, and I saw Donaghy and Lansdorf have already updated their fits, including these numbers now, which is actually a very precise number. They also measured inelastic cross-section. It's somewhat similar to what is being measured by CMS and Atlas due to event counting techniques, like the one with these vertices, which I said before. So these kind of measurements have been delivered, and I think this is a nice result from the TOTEM collaboration. But what we're going to be mostly interested in the talk, at least what I will present to you, is what the prime goal was of this machine, and going to understand the mechanism of electroweak symmetry breaking, and discovering physics beyond the standard model. And I'm sure I don't need to point out the reasons here why we believe there should be physics beyond the standard model. In fact, if the Higgs particle is where it is, probably that's already evidence there should be physics beyond the standard model. And these are the popular extensions which are usually discussed, and certainly in the experiments, highly on the experimental program, like supersymmetry and extra dimensions, but also eventually strong electroweak symmetry breakings and other models, as you see here, some plethora for them. So what will be the new physics which we would be seeing at the LHC? Obviously, there is many options around, like new type of gauge bosons you could see, supersymmetry indeed, maybe some strong interaction which builds resonances, or technicolor particles could be produced, these extra dimensions, as consequences maybe some black holes, little Higgs we heard, hidden valleys is something new that come up, many more. We don't know what is out there for us, obviously, and there is a large variety of possible signals for which we have to be ready. And there is always a certain danger in that as well, that you are gearing up to particular models which you want to, discover something, or at least test your sensitivity to. And I will have one slide on that later to show you in what way we are actually arming us against such prejudice. Now, in 2003, I had some discussion with Hitoshi on what could be possible phase spaces, what we do. We did that actually for the linear collider, not so much for the LHC at that point. And then at the linear collider meeting, and then later at this lepton photon, he showed slides. This was still in times of plastic, handwritten, what you could have here, 4 generations, even 6 generations, shadow matter, I don't know what, spontaneous quarks, super weak models, and so forth, regions not yet thought of, and so forth. This was just like an advertisement, maybe more than a joke, to tell what the possible theory space sitting at that. There's a small corner with Susie here, by the way. In the experiments, in the last 3-4 years before we got data, most of the studies on supersymmetry, and even those on extra dimensions and some other of the more popular models, were actually already carried out. So it was a bit of a sport for theorists to find possible loopholes in detection that you could have at the LHC. For example, finding very weird behaving particles which would move to your detector, or invisible particles, which are obviously difficult to find. And so we had to constantly get active in trying to counteract and see that indeed, in fact, we could eventually see if such particles would be created, we could actually detect them. That led actually, that was in a useful way, a useful thing actually, because that led also to using the detector in different ways than what we thought before. And fortunately, I should say, the detectors were in a way over-designed for what they had to do. So we could take the side paths and take, for example, slowly moving particles going to the detector, or particles that would get stuck in the detector and maybe after some seconds or maybe a week later they would explode in the detector. We could actually deal with that, and we have actually results in that. And in fact, now we strike back, because this is now what Martin Schmalstol showed at the workshop a bit, what the LHC starts to include in the physics space here. And the interesting part of this is that we're actually excluding already a big region which we haven't even thought of yet, but I think that is probably his vision. Okay, now more seriously, these are electroweak measurements and QCD measurements, which I think are very important. And if you look at it, I think like half of our publications, if not more, is actually addressing measurements of that sort. And I think some of them are really quite spectacular and nice. I will not say much about it. I will just show the small kaleidoscope of collection of measurements. For example, this is the dimuon spectrum, which we have seen already very often, I think, with all the particle families popping up here just by n-inclusive dimuon measurements up to the Z, and yeah, of course, unfortunately no Z primes yet, but we keep looking for that. Jets, which have been measured over many orders of magnitude of cross-section up to multi-TeV regions. These are jet masses up to 4 TeV or so. W and Z measurements, cross-sections of that, correlations between these cross-sections, which put the map out here. Z's going to taus, it's something essential, which you must be able to prove you can measure before somebody would believe you that you could be searching for a Higgs to tau-tau. Special features in which we can do at the proton-proton collider, for example, looking at charge asymmetries for the W's, which are very sensitive, again, to parton distributions and already being used in the FITs. And, for example, vector boson measurements with jets, which are a baseline also for gauging how well you understand backgrounds for searches which you will do, because these are typical coming in many searches like SUSY and others as a key background. And here you see one overview of bosons and diboson measurements over the top to the more smaller cross sections, and this is the level which is reached now, the 1 inverse femtobarn type of cross sections like in ZZ. And as you see, in fact, if you look at the theory, it sort of falls all well in the ballpark within 20% or so. This is a nice event from, I like the displays from our competitors here, from my point of view. These are the nice WZ event where you have one electron going out, some missing ET, so probably the neutrino going from that, from the W, and some mu candidate, which gives you a Z. It just illustrates how these detectors are working. Top quarks. So top quarks are being produced in Europe now and also being studied at the LHC. And already within the first year of really top quark physics, I would say, last year was sort of a bit of a warm-up. We reached already nice and impressive precisions on certain measurements. For example, the top quark cross-section has been measured in many channels by the two experiments here, CMS and Atlas, and now reaches a precision on 7%. This is the best measurement, is 7%. There is now a working group in place which actually is going to try to combine these measurements as we had in the lab days for other measurements. Flavor changing neutral currents have been pinned down. This is a result which constrains them more than what was done at the Tevatron. That is thanks to the fact that we have such high statistics for producing tops. We have already now a factor of 20 more tops on tape for analysis than what the Tevatron collected in the last 15, 20 years. The top gamma, top anti-top gamma channel has been seen. Top mass, this is still something which is in the realm of the Tevatron, because they have the things still better under control to go to a higher precision. We are about a factor 2 to 2.5 worse than what they are, I think, but this is a matter of time. Probably with another statistics of the full statistics of this year and the one of next year, we should also bypass that. also some CPT type of measurement, checking like the mass difference between the top and the anti-top has been found to be consistent with 0, obviously fine, but with the precision again, which is now the world's best value. In short, we have a very good picture of the standard model physics at 7 TeV, and that gives us an excellent preparation for the searches. Here is one measurement which is of interest because of deviations seen at the tevatron. That's in the forward-backward asymmetry in the top anti-top production, where the top follows more the quark and the anti-top more the incident anti-quark which came in. So you get at next to leading order, not at leading order, but at next to leading order, you get an asymmetry, and that's fine, that's expected, but what is found is that the measured asymmetry is somewhat significantly larger than the one which is actually expected from these calculations. Now, I should say these next leading order calculations are the first ones which are seeing this asymmetry. The leading order doesn't see that, so maybe it's not quite enough to have next to leading order here, so there's certainly work needed in the theory to get to a further improvement on that, but we are sitting with this asymmetry here. So, can the LHC do something on that? Well, you know, we have a proton-proton collider, so we can't exactly do, of course, what is done at the tevatron, but still, the tops mostly come from a valence quark, this is the incident quark, and the anti-tops from a C quark, which have a different distribution in rapidity, and therefore, we would indeed, if you look at the rapidity distribution as a whole, we would expect a difference there. That is less sensitive. It's also diluted by the fact that most of the top is produced in gluon-gluon fusion at the LHC, but that is sensitive to this asymmetry in the same way as a forward-backward one at the tevatron, be it not with something like 5% what you expect, but maybe only 1% type of difference. So you have to measure it much more precisely at the LHC if you want to check it there. But that has started, and both experiments, CMS and Atlas, have actually shown measurements of this kind of asymmetry measured, now measuring just the shape, if you want, of the different rapidity distributions, and some asymmetry is indeed found, but that's within the error consistent with what we find. But this is on a small data sample. This brings up hope that that we could indeed, with like 20 times more statistics, from the 1 inverse femtobarn to maybe the 20 at the end of next year, if we get this, the systematics down, have some saying on that. Particularly also since at the tevatron there is a mass dependence reported. The effect is much larger at high TT bar invariant masses. That we could check. We did not see any deviation here, so it's not an enormously big effect even at the high masses at the LHC. So the jury on that is still out from us, and of course, if it would be a real deviation and not something because maybe something lacking in the theory to explain it or something in the measurements, then that could be a sign of new physics in these measurements. Another interesting variable to look at is, or a process to look at, is the decay of the BS system. To muons. That's a rare decay. In fact, it's rare, like 3 times 10 to the minus 9 as expected in the standard model, so very rare. And again, if there would be some new physics sitting around with particle masses which are not too heavy, then they would affect this branching ratio, particularly in, for example, MSSM, the minimal supersymmetry, 4 values of a high tangent beta, because there, if you see the effects to this branching ratio, it goes to the tangent beta to the 6th. So it's an interesting channel to look at, and particularly something in the realm of the LHCb experiment. But as it happens, CMS had also targeted that with keeping its triggers and its analysis open to make sure to have this signal here. And indeed, when we looked at the data for the winter conferences, for the summer conferences here, we have something like a sensitivity of 1.9 times 10 to the minus 8. So factor 5, 6 away from the standard model part, which we actually start to get sensitive to. And of course, we would hope to see something earlier, which would then mean that indeed you see some particles running around here. This by itself led to the first combined paper from the experiments, which is not, as many people would have thought, a CMS plus Atlas paper, but was actually a CMS plus LHCb paper, combining the measurement, because indeed LHCb at the same time also opened their box and checked with their sensitivity what their result was, and in fact they found that we have a very similar result within 30% or so. So it was combined, and this is the result of this summer, which is like a factor of 3 away from the standard model limit. So we're closing in on that, knowing that we also now have 5 times more statistics on tape, both for LHCb and CMS, and I'm sure that Atlas also will start to be a player in that soon. I will not discuss more on the LHCb. I thought I would give you some flavor on their the Phi-S phase, and that has been measured, but it has been shown already this summer, and we know the value for that, which is coming out of that, which is actually a very nice measurement, but I think for time I will not discuss it in detail. Neither the CP violation seen in the charm sector, which was somewhat a surprise for some. This is the measurement of this CP violating type of measure, and looking at the difference between the kaons and the pion result in these decays. And again, they find something non-zero, which is here, the band given there. So these are very nice results. I put them just on passing here, but not going to spend real time and do them justice to discuss what I should actually deserve. Instead, I will go to the tera scale, and I will go to actually the searches and show where we are with the searches coming. And so data are coming, which create a small wave of panic in some corners in, I don't know which theory division, but I can guess. So first, supersymmetry. I think that's probably everybody's familiar with that. And particularly, of course, what I will show is that for supersymmetry, the kind of analysis which we have been doing these years, and that is there's going to be a change of paradigm, I think, in the next year or years to come on that, were maybe the sort of most naive ones to look at that, assuming that you have like a supersymmetric particle, which is neutralino, which comes out with a lot of missing transverse energy, and therefore missing transverse energy is one of the main characteristics for searching for supersymmetry. That will go on, but apart from that, we will also have to look at very many other things, and I will show a couple on that in a moment. So this is how SUSY searches have been organized in the 2 experiments. Particularly, both experiments have been dividing up the events in different categories, depending on their final states, whether they have isolated hard high PT leptons in it, and how many of them, or none, which is the simplest one, where there are only jets, but always a requirement on something missing for this LSP, which would be escaping detection. Also here we have a single lepton analysis. In the 2 leptons you can have an opposite sign and the same sign, which have different sensitivities. And new, what came out recently, is also a multi-lepton one, which can come if you have many of these gauge-genols getting into your final state, as well as photons and photons plus leptons, which are more based driven for cage-mediated SUSY type of channels. They all have a different background or a different interpretation possible in different models, so they are all important as such to look for, and you could see something popping up in one of these boxes as a first before you see it in others. In Atlas, they even go further, and they go also in the first box with Jeffy, which is just jets plus missing ET, and they divide that further up in multi-jets with 2, 3, 4 jets, and they even have a multi-jets, like I think up to 8 jets right now as publicly available. One important thing with all these studies, I will not go through detail in that, because that is different for every channel as it comes, and it's sort of tedious to explain in a short time, is that there is a strong effort ongoing in all these analyses to try to get the background, to try to estimate what the tail gives you, where you look for your signal, is driven by standard model processes by themselves, by looking at the data, not from Monte Carlo. We like Monte Carlos, we like to tune Monte Carlos, and we use them for acceptance corrections and others, but we certainly don't want to use them to tell us what the background is in these channels. And this is actually the art of that kind of measurements, if you wish to make them. So this is a picture which shows the general view of how things are going. These are here iso-squawk lines and iso-gluino lines, which you see here. And this is the region which is got with one inverse femtobarn, so by this summer, additionally excluded in the so-called M1/2, M0 plane, within given constrained MSSM models. That should be added. If we have that, if we take these constrained models, then out comes that the gluinos and squawks will have to be much, much more heavy than perhaps what we would have wished for, and sort of in the multi-TeV range, most likely. That doesn't mean that you can't have squawks or gluinos with lower masses, like a few hundred, 600, 700 GeV or so. This is just driven by the fact that we use these constraint models to represent the data here, which is something I will make a comment on in a moment. But you see the increase or the evolution from what we had with the data of 2010 to summer this year. It will not go so fast anymore now here, because now that was a real big gain in luminosity which happened here, like a factor 20 or so. Now it's still a factor 5. You will gain something, but we'll see by this summer, by this winter conferences. And maybe there's a hidden signal hidden, who knows. Same for Atlas in their presentation, and somewhat in different presentation in gluino masses versus squawks masses. So it's a bit more general how you get things, but you see also the evolution as it goes from the 2010 to 2011 type of data. In fact, all the channels, which I said before, have now been analyzed and released, and you see here a summary plot on the same type of plane I showed before, where all these channels lie. And as said before, this is within this constraint model. You see these multi-leptons, for example, do not contribute much in excluding, because that's already excluded by other channels. But in other different models, it's very important to keep track of that, because there could be, this could be the way that you actually see the signals, and you would not see it in the jet plus missing ET models, for example, because the missing ET isn't so big as you would think. So this is starting to become a complicated plot, so we now dubbed it the spaghetti monster, and if you hear about that, talking people in the cafeteria, this is the plot they mean. So, as I said, it's very important to have a language between theory and experiment of seeing or not seeing, maybe in future seeing, but right now not seeing an excess over a certain background within, a given sensitivity, what the luminosity allows us to give. And one way of doing that, and that's something we propose to theorists and discuss with them, and there may be other ideas coming up, one can think about that, is the so-called simplified models which have been used, which is reducing all of what happens actually to the essentials of what comes out in what you're measuring. For example, just plus jets and missing ET, you say, well, that's maybe only the squawk or the gluino, which is important, plus the LSP. And all else what happens before there is sort of contracted in a blob, and you don't need to know about that. So that's one way of parameterizing the results, and that is, if you do that, you may have to make a choice of mass, what you take for the lightest supersymmetric particle, and depending on that, you get these bars where these masses go 0 at this end, and they get massive there, where you then get lesser bands. But these are sort of the range of scales in a more generic way of seeing where the particles are now being pushed away from. And there is an open discussion ongoing, for example, in the CERN workshop, which I may mention. There are some interesting events, though, like, for example, the one we see here, which has a lot of jets, missing ET, similar things in Atlas, but, this could be just tales, indeed, from QCD, but it keeps us alive and looking at these events in more detail. So what's next to be done in there? Well, there is a lot you can go for, and that's, in fact, the new paradigm I sort of talked about, of thinking of what will be more, perhaps wiser measurements you could try to do for searching for supersymmetry on top of these ones, which will continue and will push to further limits because you never know what's around the corner. But one could, for example, look at more cases where you have a light third generation as the only one which is light, and so you can go specifically in there, try to find stops and bottoms, trying to do that through Bs, for example, or even tops, which are going to be in these events. There could be split supersymmetry where you have a complete different ordering and different mass levels of things you can compare. Of course, RP violating SUSY has to be looked at as well, and so forth. In fact, some of these are already been looked at, as I will show. So, in some workshop which is running, if there is interest also here to participate, there is running since August going up to June 2012, discussion on the implications for TV scale physics where these things are, for example, reviewed. That's also some workshop which has as aim to write a report for the European Strategy Working Group for High Energy Physics, which is meeting next year in September in Krakow. And so there are a number of new measurements, like, for example, the multi-lepton analysis. Now, multi-leptons allows you to beat background, which is mostly the QCD background, without having to make a missing ET type of requirement. And that is therefore complementary to the kind of searches which I showed before. And there was a little of excitement on the blogs about that because some people saw some two significances again, two sigma significances, but given that we have 54 categories of which you look, you must be starting to see these kind of things. So it's good to watch that space, but not yet good to get excited about. And this is the other part, looking for third generation more specifically, for example, tops and bottoms, bottoms quarks, through, for example, detecting B quarks or excesses of B quarks in these events, which looks with a lot of activity and also a bit of missing ET in there. But nothing found there. There are gauge-mediated SUSY searches looking for example, photons particularly, as I mentioned, plus missing ET, maybe with jets on that. And there's a special angle of that. Sometimes these lifetimes could be a bit longer, such that this decay would actually happen in detector. And that's not this analysis which is shown here, which gives these limits as given there. But we also look at that, and I'll show that in the special section. Okay, for SUSY, so far, this is where we are with SUSY, so no particular signal for that yet. What about extra dimensions? So probably you will hear more, or you have already heard on this in the past days, so I will not give too much on that, but this is the case, for example, when gravity could become strong in one of the particular models. And as I already said, in tribute to ADD here, we looked also to this channel where, in case you have, it's just gravity, which is getting extra dimensions to expand, and it could become strong. You could get towers of gravitons being coupled to our normal particles, and therefore you could, for example, produce in a proton-proton collision monojet type of events, getting a gluon out, being balanced by a graviton which goes undetected because it's interacting weakly with detector. So the limits there, we'll have looked for that. You would find this kind of excess you would like to see on your data if you would like to have this model or this kind of theory. But this is the data, and the underlying histogram here has what we derive from the backgrounds, and you see there is no excess to be seen yet, which gives that for this kind of new Planck scale closer to us, it has to be either above 2 to 4 GeV, depending on the number of dimensions which you would allow for. So the lower one is for the more dimensions. But you get nice events when you look for that. This is a monojet event. You see really one jet of 600 GeV sticking here in the detector, and there is really nothing else apart from the soft particles here. So this jet sits here. Can that happen? Yeah, that can happen. That could be, for example, a Z boson plus jets, and the Z decays into neutrinos. That would give you such kind of event as well. So it's always something you have to look with above the background, which you have to estimate from your data. Also for Randall-Sundrum type of resonances, in this case for the photons, so that if you would see something, we would at least not confuse it with Z primes, for example. we look at the diphoton mass spectrum, you would expect some peak like that to sit up here somewhere, nothing particular above the data, the estimated background. And this is a new one. This is again an ADD one, but this is looking at dimuons and looking at the interference which can happen here in the diagrams when you have normal gamma star Z exchange or a graviton exchange here. That should change the spectrum as well, but change it's only in the Monte Carlo right now, not in the data, as you see. And again, we have very competitive limits with what we have here, although this is on MS, which is a mass cutoff scale. It's not really the Planck scale. So we don't see them here. And thought my laptop went to sleep. Okay, and nevertheless, while you would expect, for example, something like a possible micro black hole to be formed, where you would need at least some of the Planck scale arguments that they are be brought into the TeV range, and we have not observed yet. On the other hand, looking for these particular micro black holes could be another way, and maybe even a faster way, of seeing some extra dimensions appearing. And so that's another sort of search which we look for. And of course, we look only for friendly black holes which are decaying in 10 to the minus 27 seconds, so our theories tell us, and they look like sort of like a spherical ball blowing up. It gets distorted through the kinematics here, but that's basically a lot of the initial energy of the PP collisions would come back in some kind of a very distributed way into detectors. And the variable to look for that is the scalar, the total scalar transverse momentum you find, or transverse energy you find in the detector, and you look at the extremes where you would see if there were black holes, some onset there. Again, we don't see that here. And although we can set now limits on that, I should also add that there's quite a bit of controversial on the cross-sections of these black holes. So it's we just see no events on there that people can then calculate themselves what for cross-sections that means. But you get very nice events, for example. This 10 jet event here is selected by this type of criteria. But it could happen in QCD. You have a 10 jet event with a very small ray. Now, there are many other searches, and this is just a list of what I give here. And in a normal talk, say before last Tuesday, I would just go and bore you to death with not seeing any of these particles here. So I decided, bit changing that for this talk here and the one yesterday, that I will not go through these type of measurements, but go to something where what was that we heard on last Tuesday. Before that, however, I should repeat that we invested quite a bit of time in actually also looking for very specific signatures which are very unusual. For example, here in this kind of split supersymmetry, which I think Savas gave to us at some point in time some years ago, we're still suffering from that. So, for example, you could have particles changing charge as they go through the detector. These heavy particles, these are Haar hadrons, which are formed by a long-lived gluino, which you get in split supersymmetry because the squarks are at very, very high scales, 10 to the 15th or so. While interacting through the detector, they can pick up charge and then change it and flip. And that's something, for example, our reconstruction program doesn't like too much. So we had to do some special things for that. Other scenarios are gravitino dark matter, GMSB, hidden valleys, which could actually have particles just splashing in the middle of your detector and are invisible for RPV models and so forth. And even some particles could actually stick in the detector, or in the walls for that matter, what we thought at first of studying, but stick in the detector and sit there for a week, and then suddenly completely disconnected with the original collision, they splash open. In fact, for that, for example, we keep our detector alive also when there is no beam, when there's no collisions in the machine, so that if we would see something, at least in the calorimeters, we would be able to get that. And we've produced limits on that, but I won't talk about it today because they are already from this summer. This is something new, which we had, and this is looking for this type of GMSB models where you have a a neutralino, which is not the lightest supersymmetric particle, but in fact the gravitino is, and this neutralino will decay in a gravitino and a photon. But it was produced here, it moved some way, and then the gravitino got ejected and the photon got emitted and is detected by a detector. So, what happens is this photon is not coming from the interaction vertex, so these are displaced photons you have to find, that, of course, makes this analysis a bit tricky, because photons don't leave a track, you can't actually measure the direction. But we do that now with techniques in both experiments, using the shower shape which we see in the detectors here, in our case in the crystal calorimeters, to deduce that that is incompatible with the photon coming from the vertex here, but it had to come from some other vertex. Of course, pileup is not making that story easier. But still, this is what the data shows as the displaced vertex type of measurement, and this is what you would expect from a particular GMSB model. And so far, we don't see evidence for that. And something similar for Atlas. I won't particularly go to that. This is a grand summary if you would like to see what we've been looking for fourth generation stop particles, leptoquarks, and whatever has been looked at, and the limits which have been setting so far. So nothing of that has been seen up to scales of a few TeV in some cases, particularly in the colored objects. That's a similar one for Atlas. This was for CMS. This is a similar one for Atlas. So if you have a favorite channel you would wish to look at and see what the state of the day is, you can find here by how far it has been not seen. And that brings me to that one point which I mentioned, is that what about missing something? Is that possible? And for that we have this kind of sort of fail-safe type of mechanism. That is, we take the events, we actually throw the events exclusively in baskets, depending on what the content of the event is. For example, there's one electron in there and one photon above a certain threshold, or one photon and 3 jets, or 2 muons and 1 photon, and so forth. So each event falls into some box just once. And then, and this is so far something where indeed we use the Monte Carlo, because that's not so easy to get a data-driven technique for that. In this, like 20,000 histograms or so you have to look at, which you could get here. Well, you make histograms of some variables of these objects you have here. For example, the total PT, the invariant mass of all these objects, the missing ET associated with that, just to name 3, and that you have for each box, and you have many of these boxes, and you have many of these histograms to look at. And they are automatically compared with a prediction of standard model Monte Carlo in this case. And if something turns up, then some alarm goes off, and we look at that. Usually, of course, we found so far that is then something missing in the Monte Carlo or something wrongly described in the Monte Carlo. We can then adapt that and go ahead. But each jump in statistics, this will be watched. In the 2010 analysis, we didn't find anything spectacularly excessive. So for the searches, in fact, the summary is very simple. You need to remember so far only 3 numbers. And they are simple numbers. 1, 2, 3. So easy to remember. You only have to remember for what. SUSY is somewhat with the 1 TeV scale, where we are starting to exclude things. Gauge bosons, like Z primes, W primes, 2 TeV type of. And the colored objects, like excited quarks, is about 3 TeV. This is where we presently put limits in a very severe summary. This is again Hitoshi. You feel that I like what he sometimes produces. He said he's a theorist, so he can do that. I could never make that joke, but he can. So how does it feel to be a BSM theorist? And that he presented in CERN in October at the ICFA seminar, where normally no jokes are made, but this is a very serious thing. And, well, he felt like that. All right. So I have still a bit of time left, I believe, so I can tell you now on the hunt for the Higgs. The key question is, where is the Higgs apart from these pictures which we have of Mr. Higgs in front of our detectors? Where is it hiding? Now, one thing, before we start with that, I should warn you and remind you that there are 3 kinds of lies. There are the normal lies, the damned lies, and statistics. It's a health warning, because statistics is much of the game which is happening now with these Higgs searches. And for that, maybe I should warm you up with the sort of plots you're going to see. You're going to see plots which shows local significances testing the background hypothesis. If what the distributions we see are compatible with the background, you're sitting here typically between 1 and 0.5 or something like that. If you're not compatible with the background, you see something jumping like that. And then that's the level of significance you're not compatible with the background, which you can quantify. The testing of a signal hypothesis we do typically with the so-called CLS type of variable, which is a normalized one to the background one, and you will find plots saying sort of 95% confidence limit on the sigma, so the cross-section for standard model Higgs, for example. When you cross the line of 1, you start excluding, and then you have the expected value with 1 sigma and 2 sigma band around it for the different colors which you see, and then you see what the data does. And then you get chills when you maybe see a peak like that, which is jumping up. The last thing is that to measure the signal strength, which could be in the data, by varying a parameter mu, which is saying with what would my data be most consistent as a cross-section for the signal injected in that kind of analysis. And then you see, for example, if you're sitting around 1, this means you're compatible with the production of a Higgs mechanism, a Higgs boson at this statistical level. Just to get that clear. Now, this is what the searchers did. We have these channels here, which we search for in the low mass region, and these in the high mass region. I think that's all well known. The production mechanisms also mostly gluon-gluon fusion. Then the VBF gets dominant, and DIF gets the next one in line. But sometimes the associated one is very useful as well for background reduction purposes. The top we're not actually using yet. This was the situation as it was in 2011, in August 2011, at the Lepton Photon Conference. So this is the plot, as I explained before. Below the 1 line, you are excluding. This is the expected value, and you see the dance of the data around the expected value here, although always being a bit on the high side in the low mass end. That was for Atlas, similar thing for CMS. The important message of that was the regions we could be excluding, which were sort of disconnected regions because, the data jumps over the limit equal 1 line. But in Paris, the data got combined, and then you see all this range here. We stay below at 95% confidence level. If you're more demanding and you say, before I talk actually about an exclusion to be 99.99%, then, well, that's a different story. But it doesn't really matter a lot, as we saw. If you go, for example, from 95% to 99%, the border here changes by GeV or so. So the next stage was the full analysis for the data as presented last Tuesday. And this is the CMS part of the story, where these are all the channels which have been readied with the full data set of last year, be it a preliminary form, so there are still some small tweaks and improvements possible, but this is the bulk of the message which is sitting in our data, given by these channels here. And I will just flip through them quickly because I want more to discuss the global picture rather than the individual ones, but to show we have measured in all these individual channels, for example, the Higgs going to 2 Z bosons, to 2 leptons, plus something else, neutrinos, quarks, or taus. These are particularly channels which are driving the high mass searches, so they're probably not so exciting right now, although we keep improving them because you never know, what's beyond the standard model, what you could find. So it's not just excluding standard model Higgses here, which is the name of the game, but we have to go further with that as well. But anyway, these have been done. The tau channels have been done. These are already more interesting because that's a channel for the low mass, and that's been analyzed in different ways, either with or without jets being associated, and even B quarks being associated, which is particularly sensitive to MSSM type of Higgses here. And there we get a nice exclusion plot, which we see here. But this is the, wrong direction. This is the standard model Higgs analysis. The one thing, and which will actually be coming back in several of these plots, is that you will see, this is the expectation, in several of these channels, if not all for us, the data is always somewhat above expectation. In this sense, it's 1 sigma. By itself, not considered to be significant, but in the bigger picture, it starts to count for more. So we see this is our exclusion limit. We can't exclude as much as we would expect with this channel, even though we are a factor 3 in sensitivity away from the standard model cross sections. BB channel, that's a very difficult one because there's a lot of B's around in these data. So we only study them in association with the Z boson. So you take a hit on the cross section, but you gain on the purity, and it becomes actually possible to do that. And you see again, this is the result expected, and this is the data as you get in. By itself, not particularly significant. I should, by the way, say that the wave function, if you want, of a signal that would be injected here goes all over the plot. So any mass, we have no mass resolution really in this kind of measurement. The same for the taus. It's about 20 GeV or so, which is actually the full width of this plot essentially. So any signal injected here would give you something like an excess over all the points, the mass points you see. WW channel, which was a bit in flip-flop for the earlier conference results, but I think we have been studying that in more detail, and there is no way to have to change that. So these are results. You see some agreements with the data in the different variables here, or in fact these are different channels, W's plus 0 jets, 1 jets, or 2 jets, and the W's go into charge leptons, and the missing ET you see. We use kinematical variables which would enhance scalar particle decays and so forth, a typical event here, and a result here. And again, you see about a sigma higher in the low mass range than what you get. Now, the interesting channels, of course, are the multi-leptons ones with the 4 leptons, 4 charge leptons. This is a nice 4-muon event, for example, coming from 2 Z's decaying into each 2 muons. There, CMS has been pushing more on the limits to get more acceptance in these, going to lower masses by going to lower lepton PTs to increase that. But the important thing is the result here. This is the spectrum which we have. And we see like 72 events expecting 67 plus minus 6, so that looks perfectly all right. In the low mass range alone, that was the full mass range before, we have like 13 events expecting 9 plus 5 plus 1.3. A little high, but not much really. Of course, some things draw the eyes, like for example, you see 3 events aligned here, be it at the mass, which is not the most talked about in the newspapers. And this is the result. And again, you see the data pushes a little higher than what you would expect in that region. So, the 2-photon channel, that has this kind of excursions, with one excursion sitting around 123, 24 GeV or so, where we go a little out of the 2 sigma here. And that's actually interesting, although by itself not meaningful, I would say. Just seeing that, it's not concluding anything, but that's exactly also what the strength of a Higgs would be in here, that we will see a bit later. By the way, this is the best calibrated channel with about 1% of energy resolution in here. If you look at the raw data, maybe you don't see this sitting here immediately. You see some jumps up here, and that therefore we say this could be still statistical fluctuation. But there is this going up there. Okay, this is all the channels together. This is another type of spaghetti plot, so I will not go too much on that, except that you would see the global thing that indeed everywhere you see a little enhancement. And this is the sum of all the channels together. And here you see now that in this sum here, you have sticking something a bit higher. How significant is that? Well, if you look at these p-values, which I introduced before, we see, in fact, we have two peaks in CMS, one at 19, given by these three events from these ZZ events which we had there, and one of the photon events which are sitting here, and that is 119 and 123.24 basically. The maximum local significance we have is about 2.6 sigma. So this is still not something you would find spectacular at that point. And particularly if we were to include so-called look elsewhere effects, which statisticians always force us a little to look at, saying, you know, you have a peak, but what is the chance you get the peak everywhere? So you have to introduce a penalty factor. It goes down to 1.9 sigma. So the excess we see in that low mass region is of modest statistical significance and could be reasonably a fluctuation of the background. But we can of course see now what would it be if you would include the signal as well. And that's given by this line here, this blue line. This is against these local p-values. And this blue line gives you what you actually would expect to see as a deviation if there were a Higgs sitting inside. And sort of that, the tantalizing thing is that is exactly, of course, at the right level. It doesn't prove anything. It still can be some statistical fluctuations here, like, for example, this one should be, because that's very far away of the enormous excess you would expect the Higgs would be giving you in our data. Here we are sort of at that line. And if you go for the best value, as I said before, we find here an injection of this suppression parameter mu to be equal 1, so the cross-section to be that of the standard model Higgs particle, to be most compatible with the data, be it with the broad band of uncertainty here. Yeah? We should not forget that. That is where we need more statistics to get that done. Okay, let's quickly look at Atlas. So Atlas had also many channels analyzed before, but they have updated basically only 3, the WW, ZZ, and gamma-gamma channel. And for the rest in the combination, they will use what they had for the one inverse femtobarn before. So we see the WW channel here, and they find something which, you know, you also saw back a little in the CMS plots here, which is of the 1 sigma outside higher than the expectation here. But nothing particular in the local p-values plots. It's all below 2 sigma, whatever you see here. It's the same what you see there. For the Higgs channel, there they actually have, and I showed these plots already to illustrate the statistics. This is this small peak which you see here, which sticks out, and which sticks out up to almost, well, by itself, 2.8 sigma or so, 2.8 it is. That's interesting. Now, looking further to the next channel, there, the third channel they've included, the ZZ to 4 charged leptons, they see something, first of all, which we don't see in CMS, that there's some accumulation at the higher masses. That's to be discussed some other time. But what they're discussing now is these 3 events which you see around 125 GeV or so. And that lines up not too badly with these 2 photons excess which they're seeing. In fact, this is more events here, but of course 3, so 3 is a small number with a large statistics error. It's more than what you would expect to see at this point in time, even if there would be a Higgs signal. So they could be a bit lucky in that sense with the events they get. And this is a nice event which they get for the 2E, 2 mu candidates, where you have the mu sitting here, the mu sitting here, and the green guys are the electrons which just sit there. Okay, I'll probably skip that for time, but compatibility with background, for example, of those Z events are giving here of the order of 2.3 sigma. You see that there is an excess over there. So putting the Atlas data together, that is their total plot, and this is the low mass range where they see lined up, sort of enforced from their 2 channels sitting very close to each other, giving, I think it's in total, it was said here, 3.6 sigma effect, which, if you include look elsewhere effect, also gets penalized, which is probably said on the next slide. In fact, it's interesting in Atlas that they also had a downward fluctuation. I didn't stress that in the 2 photons here, just around this region where we had the lab limit at 114. So they actually are starting to also address or exclude some more at that lower range. This was what was known before, and this is now with the Atlas limits what is being excluded. So a little bit also here, and here now up to 130, that is with this 95% excluded. Similarly for CMS, it's 127 or so, but very, very similar. But in there is sitting this. And so, as said, it is not something which you could think is by itself evidence for a Higgs as such, but it's very tantalizing that, because it's exactly, as I said before, the way a Higgs may actually start to show up in our data by just a small excess. And obviously we're going to need this next year's data to look into that. Now, one thing which certainly the chairman still wants to see is how do the two experiments compare. So I kept that basically for last. This is the excess, the local excesses which we had, 3.6 for Atlas, with the look elsewhere effect, 2.2 to 2.5. In CMS, we had 2.6 going to 1.9. This is not mine, but this was presented by Tony Doyle yesterday at another Christmas theory workshop. So there are Christmas theory workshops all over Europe these days. And this is the two data points, so try to match as much as possible. I should say, don't expect an official combination soon, because that will be done only when the experiments have published their results. But still, this is what we have. This is the thing from CMS. This is the Atlas one, which is stronger and said even a bit too strong to be a Higgs, but they could be lucky. It's small numbers, small data. And, well, you can draw your own conclusion whether you believe that aligns or amplifies each other. Okay, and I will stop here just saying, well, let me basically stop. I think this is the last slide, which I'll show. This is, I think, our Apollo 10 moment, in a way. Also, that is not my, that I got from Tony Doyle yesterday. So Apollo 10 is like a dry run. They went around the moon. They did not land on the moon. So you couldn't actually say, you know, the Eagle has landed because it didn't land on itself. I think we're in a similar situation. This is a dry run. We haven't landed on the moon. We haven't seen the Higgs yet with confidence. We will not have it from the 2011 data alone, but there is something tantalizing. There is some excess. There is something we have to clarify with the data that's coming next year. And particularly, we're going to have the LHC running and giving us, hopefully, between 10 and 20 inverse femtobond by the end of next year. So 4 times the statistics. That should clarify this fluctuation we have there, whether that's something real or not. And I think I'll stop here and I'll leave the rest to read. Okay, thank you.
Thank you very much for these very nice results. Let's ask for questions. David. Microphone there.
So, first of all, congratulations. I mean, that's fantastic. But as a naive theorist, could you explain to me why, when you're looking for a signal that you've been looking for decades, in channels which you know ahead of time, what I am amazed at, amazing control over systematic errors. Mm-hmm. Why, when if you combine the two of you, you have essentially a 4 sigma observation of what we might very well expect.
All right.
Why
Yeah.
can't I believe what the mathematicians tell me about probability theory and 4 sigma?
So I'll tell you. It's that's probably a fundamental difference between a theorist and experimentalist. We give out data right now, and there is the word preliminary on it, and that has reasons, because there are still things being cross-checked, still things being optimized, still things being done. So I don't think personally that it will change the picture a lot in the next few months, what we'll be doing. but there could be changes. So there is no point from us to invest, and it's really an investment. You can do it with a ruler, and you can probably find out what and you're going to be right within 10-20% of what the significance is. I take it for that. But when the experiments are going to make a statement, that is going to be taken very seriously. And we want to do it only when we are entirely finished with that analysis. So this is the preliminary version, and it should be coming soon, because we plan to publish somewhere just after New Year, maybe end of January or something like that. So I think the winter conferences, we can discuss a combination from the experiments. But just being prudent and doing the job at the right moment in time, which means when we actually fully completed it.
Wasn't really the question. The question was, given that 4 sigma means that that's one chance in 1,000 that you haven't seen anything? Is that what it means? And if not, why not?
No, I am not arguing with the statistics allowance what the 4 sigma means. So
3.6 sigma
yes,
means one part, what is it, 3 parts in 1,000?
something like that. It actually was written on my slide what it exactly means.
So have we seen
That-
the Higgs?
You know, pentaquarks had 6 sigma.
But there,
In
that
several
was not
experiments-
something you expected, and you had no control over systematics in the way you do now, right?
No, but I'm just saying 5 sigmas or even 6 sigmas come and go away. And,
When-
5 sigma is our
when-
threshold usually in our community. So I think we keep to that.
So that's the answer that's often given. We have
That was an automatic pilot that I said that.
we have a disgraceful history as a community, right? But is there an example of something where, like this, where we knew what we were looking for? We knew what channels we were looking at? The machine was designed to do this, and you've been working on the systematics for years and have...
So it's becoming a little philosophical because it depends on the level of belief. For example, the top quark, they were seeing evidence already with 2.7 sigma or something like that. But that's a different perception, I guess, because that is indeed something which we knew would have to be somewhere there. The Higgs, I think, not everybody is yet as convinced that that may be there. So we still need to convince the community that it's actually there. And for that, I think I would really trust it when we see it and we say, well, now we can really exclude that that's a fluctuation. Because we still talk very small number of events. A lot of that part, what you saw of the peak here, is 3 events, right? Just 3. Throw pigeon balls, and you see how
I know,
it
but
can
remember,
happen.
there was only one omega minus event.
I know.
Well, perhaps I am personally rather happy that experimentalists are very cautious and do not jump on results because we theoreticians are convinced that something should be there. Now, we have seen results with 2 or 3 sigma coming back and disappearing, and therefore the fact that they are cautious and they want, by the way, nobody's rushing behind them. They will collect results. The incredible thing is that we have 10 to 20 femtobarns next year. I believe that we will be much more sure, and then themselves will be, when the result will clean up. I believe that let them work. It's not a bad idea.
Maybe I could ask you, what are you worried about?
That the result is not there.
That statistics plays a trick on us.
Okay. Belén.
That's why I put this slide on the lies and,
Just very simple, precisely the number of events. So there were like 3 events in Atlas in 4 leptons. How many events are we talking about in Higgs 2 gamma? I mean, what excess events over how many?
So that's a different story in the Higgs 2 gamma. So in ZZ you basically have no background, so each event counts. While we have a couple of thousand events in the Higgs 2 gamma. In that peak which you're seeing, it's probably of the order of 100, and then you have fluctuations over there of 100 to 200. I mean, I could even go back to the plot to show it. Maybe the Atlas plot is the one that shows it. So here that's 400 events. You see 3 bins, so that's 1,000 events, and you sit on top of that.
Okay.
Álvaro.
I'm going to ask an Apollo 13 question. Can you go back to your transparency where you first mentioned the look elsewhere effect in CMS?
Probably here.
Yeah, thank you. You see, there's a big difference between having looked elsewhere or having looked only here. I understand personally very well the statistics behind the result after you have been looking everywhere where you're looking. Doesn't matter whether it is one of the ranges or the other, but on a big range. The maximum local significance is for looking there where you have seen a signal. It's an a posteriori probability. It's the enhancement at that point where you have seen the signal, which you hadn't seen before you saw it. So
Yeah, I'm still with you, okay, yeah.
the
But
big
that's sort of like
significances,
here.
the big significances that you give have an a posteriori component. They are local, and therefore they are at the point where you're looking when you know where to look. And a posteriori probabilities are completely meaningless. For instance, the probability to see what you saw is 100%. Nobody cares about that. So these big numbers are a way to present the data, not very convincingly, so that it looks much more exciting than it actually is.
I was thinking you were going to say the opposite, but okay.
No,
So
the
I was not
opposite was
completely with you.
the opposite was already said by David.
So actually for that thing, you know, for me I find look elsewhere effect a little philosophical, but
No, it's the only
since we
correct
do-
statistics.
No, in statistics it's a different story. In statistics you can do it correctly. It's a way that if you have to apply it here or not, that can be discussed if that's correct or not. And therefore, for example, there are voices that say, well, you should indeed look only elsewhere in that region where we know a Higgs could still live and not at the full range. And therefore we give different numbers like that. And you can judge. You may wish to believe neither or any of these results, or you may weight them down or give them different penalty factors. Therefore we give that information.
Is that the local information given your 2.6 sigma implies that you have known where to look. And that is not a correct statistical question because it's a posteriori. You have decided a posteriori where to look, and there is a 2.6 sigma.
Right. So, but local is what it is.
Wrong.
Yeah, but this is what is the global probability. This is what you want to address. And therefore you can get there, and that's of course not as high as what you have in the local probability.
Yeah, but the first one should have never been quoted because it's not convincing statistical.
Oh, so somebody would certainly read it off our plots and publish it if we would not quote it. Because that is
an
the obvious thing which you see.
extremely weak reason.
No, I don't think so.
Well, I do.
Because they would probably do it wrong. So anyway,
Oh, if it is to be done wrong, you better do it yourselves.
we better do it ourselves and we give the right number, but we don't say that that is the number of the significance of a putative discovery. I mean, I hope you followed the rest of my talk. I actually played down that number myself, saying that, you know, this is what, if you look purely at these events, but there's like 3 events here or there, and it's indeed just at one particular place, and that is not convincing by itself. And therefore, even if that would be going over 3, we would not treat that as a 3 sigma evidence. Atlas sees 3.6 sigma. They don't use the word evidence at all, which is typically something you use if you work over 3 sigma, precisely for these reasons. So we are fully aware of that. And therefore, we give these other, you know, values which you can, and you may choose whatever you want from these, according on your, but they are not wrong. By such, these values are mathematically correct. The interpretation is where you can go wrong. But we don't interpret it as a Higgs.
I believe the conversation is very good. I believe there is one in the back first. Doubtful.
Coming your way.
Thanks. So the theoretical understanding of, from what we understand about micro black holes is that they are particles, basically. They are quantum particles, the first ones. So why are you constraining them by looking for multi-jet events? This is what I never understood, because multi-jet events, you can look for the ones which are already good, in a good approximation, classical. There is no chance LHC can produce those.
We've discussed that before, and in fact, You will be very happy to see our next paper coming out, which I wasn't allowed to show yet because it's still in rotation, where we start from 2.
Okay.
The minimum, and
That's-
we include that part. Now, actually, here we used it, and we started from 4, but we used the 2 to estimate the background. But in fact, in the next one, we already start from 2, so we
Oh,
do
fantastic.
everything and the whole range. So
Okay, great. Thank
There
you.
was another question over there. No, yes? There, yes. No? That was.
It's just a technical comment. If you go to any of the confidence levels with the green and yellow bands, please. I understand it's misleading the way the results are presented, because if you calculate what you expect for a real Higgs signal using whatever method, 2 experiments or whatever, the expectations has error bars like the green and yellow ones, which are similar in size. Okay. So
You mean
if
the,
you just
the Higgs cross-section, you mean, or?
no, it's not the error in the cross-section. It's the Poisson error in your estimation of the expected limit in the signal plus background case. So maybe this is not the best plot, but you saw one with what you expect for a signal in this plot. In number of signals.
Oh, you mean this one?
Well, anyway, I mean, the expectation has an error band which is similar in size to the band you get in the background. So when you have both bands together, we never draw these bands because then it's impossible to read the plot. But at lab, sometimes we did the opposite plot. You don't quote the bands for the background only experiments, and you quote the band for the signal plus background. And then you see that this 3 sigma is not a pure number, because it's not a precision measurement of the 3 sigma. This is just it's a confidence level.
Yes.
It's where is the edge of the error bar on an observation, and this has a wide error on top of it, which is never shown. That's why it's difficult to interpret those plots.
I'm not actually sure, because the errors, for example, these things are done typically with toy experiments to get the binomial type of distribution which you get from that, and errors on cross-section, things like that, they are fully propagated in there. Maybe you mean something else, and we can discuss it offline. But
Yeah, that's why I say it's too technical. What I want to say is
Okay.
that I understand the confusion
I
interpreting the
believe
data
we
because
should
it's
move
not
on, please.
clearly.
Antoniadis, next question. No. Yeah.
I have a practical question for next year. Suppose that every experiment gets 20 inverse femtobarn. Would it be possible to claim a discovery of 5 sigma in the whole region, which was not excluded this year?
with 20 inverse, according to what we
Did this
expect,
exercise?
yes. I mean, according to the expectations, yes. I mean, fluctuations are what they are.
Even if
but-
it is not 125, but suppose that
But
it's
maybe it's
lighter,
at 116 or something like that. Yeah, should cover the full range.
without combining the 2 experiments.
I was thinking certainly with combining. Without combining, should be. We always said that would be between 10 and 15, so 20 should be good. Particularly if you're running at 8 TeV, because then we got even a bit more. And then I think 10 at 8 TeV was enough for a discovery.
Yes. Last question, please.
So I go back to these bands, the predicted bands for one of the channels. I mean, I guess like in gamma, you have some measurement of the background. So this is based, I mean, essentially the 1 sigma that you plot there in this band is statistical error, essentially. Is that correct?
No, it's everything. It's also the theoretical error. Everything is included in there.
Yeah, but there are other channels where presumably systematic errors are much more important because you cannot measure the background in the data, right?
Right.
So let's look at one of them, like H to gamma, where you have really, a band which
No, this
would
is
be
the gamma one.
statistical. There you have fluctuations upwards and downwards, right?
Right.
So I guess the binning here is important, and in particular in the gamma plot of Atlas, you had some large fluctuation, and then then next to it, fluctuation
Yeah.
going down. So if you bin differently, the peaks will move around.
In
Right?
fact, not. They may move, but by half a GeV or so, not more than that. because we're talking really the resolution here. I mean, the binning is driven by the resolution of the detector. So we have a 1 GeV type of resolution, the best channels to going to 2 GeV, and then the worst channels. So it's a bit in between here what we're having. So the exact mass value, if you say about that, if you really let it loose and where it will find, if it will be 123.5 or 123.7, yeah. There are, but not more than 0.5 GeV, for example.
Of course, the fact that you have fluctuations downwards also beyond the 2 sigma level.
Yeah. No, we're not hiding them. They are there. That's right.
Well, I believe that we should close this experimental session. I believe that we really should thank to the LHC people for the splendid performance of this machine that really opens up this new thing, and also to our experimentalist colleagues who have worked so hard to extract data, and a lot of hopes that with this new luminosity that you will have, you will be able to convince us all that you have found something that we're expecting to find. Thank you very much.